Let us see the definition finitely generated extension. An extension E of f is called finitely generated if there exists a finite number of elements u1, u2 and so on ur in capital E such that the smallest subfield of E containing f and the set 1 u and so on ur. It means capital E is an extension field of f and there are some elements alpha 1 comma alpha 2 and so on alpha r that are belongs to capital E such that E can be written as or E can be generated by f and the elements 1 comma u comma and so on ur. In such a case we say that E is finitely generated by the elements u1, u2 and so on ur over the field capital F. Here very clearly you can observe this sequence. Uh, Capital E is an extension of F, but in mid there is another extension capital F of alpha 1 comma alpha 2 comma and so on alpha r. That's it. If E is equals to 1 comma capital F of 1 comma u1 comma u2 comma and so on ur, E is generated by F and the set 1 u and so on ur containing the set 1 u and so on ur, then we say that this one is finitely generated extension of capital F. In the next theorem, depends upon the same definition. Let us see. Capital E is equals to capital E is equals to f of u1, u2 and so on ur be a finitely generated extension of f such that ui, where I is equals to 1 to and so on smaller, are algebraic over capital F. Then E is finite extension over capital F and hence an algebraic extension over capital F. It is very simple. If you show that E is finite extension, obviously every finite extension is algebraic extension. So let us start our proof. Capital E is equals to f of u1, u2 and so on ur be a finitely generated extension of f such that each element u1, u2 and so on ur are algebraic over capital F. Our aim is to show that capital E is finite extension of f. To prove this, let us define a set. Ei is equals to f of u1, u2 and so on ui, where I is less than or equals to r, lies between 1 and r. I varies from 1 to r. By using this definition, E is superset to f of u1, u2 and so on ui and is superset to f. It means capital E is extension of capital F. In between them there is another extension. Ei generated by the f of u1 comma u2 comma and so on ui. It means there is a sequence like this, extension field sequence like this. So right now, by using this definition, they are one of the superset to. So f is subset to f of u1, u2 and so on ui and it is subset to capital E. So right, this shows us f of u1, u2 and so on ui is clearly an extension of f. By data, ui's are algebraic over f of u1, u2 and so on ui. Ui's are algebraic over f of e1, e2 and so on ei means let us name it as ei minus 1 with e naught is equals to f. It means you can write ei as ei minus 1 of ui. Now consider this is not equals to, this is dimension. The dimension of ei over ei minus 1 is equals to the dimension of ei minus 1 of ui over ei minus 1. It is equals to ni. Say this is, we are taking small ni as a number. Just we are choosing that number, that's it. So which is a finite number. We know that there is a previous theorem. If f subset to are equivalent to k subset are equivalent to e, then dimension of e over f is equals to dimension of e over k into dimension of k over f. By using this property, here dimension of E over F is equals to dimension of ER over E naught. It is nothing but dimension of ER over F. It is nothing but dimension of ER over ER minus 1, dimension of ER minus 1 over ER minus 2, and so on, dimension of E1 over F. We define that each dimension is Ni. So here it is Nr. The next dimension is Nr minus 1. The dimension of the last term is N1. I think everyone is, we define that it is a finite number. So the product of finite numbers is also a finite number. It means dimension of E over F is M1, some finite number. It means E is a finite extension of F. Therefore, F of U1, U2 and so on UR is also an algebraic extension of F. Because we know that every finite extension is an algebraic extension. And here we show that finitely generated extension is finite. You have to understand like this here. I can write the sequence. Okay, we take one more page, additional page. Like this. F is subfield of f of u1. It is subfield of f of u1 comma u2. It is subfield of f of u1 comma u2 comma u3 and so on, f of u1 comma u2 comma and so on ur minus 1. This is an extension of again capital E is equals to f of u1 and so on ur. From this sequence you can conclude that the dimension of f of u over f is a finite number, say it is n1. The dimension of f of u1, the dimension of f of u1 comma u2 over f of u1 is equals to n2, another finite number. In a similar manner, we define that the dimension of f of u1 comma and so on ur over f of ur minus 1 is equals to nr. So now the dimension of E over F, the dimension of E over F is equals to the dimension of ER over E naught. This is nothing but the dimension of ER over ER minus 1 into the dimension of ER minus 1 over ER minus 2 and so on, the dimension of E1 over F. So that's why the product of finite numbers is become finite. So if it is finite, then E is equals to f of u1, u2 and so on. R is a finite extension, and every finite extension is an algebraic extension, which is required one. That's it. Right. Now we prove another theorem. This is the last theorem of this topic. Right. Let us see the statement. It depends upon homomorphism. Before going to do the theorem, let us see the definition of F homomorphism. It is also known as embedding. Let capital K and L be an extension fields of F. Both are extension fields. K and L are extensions of F. K and L are extensions of F. K is an extension of F. L is an extension of F. Now sigma maps from K to L. Sigma that is mapped from K to L be a non-zero homomorphism of K to L defined as sigma of A is equals to A for all A belongs to capital F. Then this sigma is called embedding of K into L or F homomorphism of K into L. Remember that both K and L are extension fields and there is this mapping sigma that mapped from K into L, which is a non-zero homomorphism and defined by the condition sigma of A is equals to A for all A belongs to capital F. This homomorphism is known as the embedding of K into L or F homomorphism. So depends upon this definition, we prove a theorem. Let us see that. Let capital E be an algebraic extension of capital F and sigma maps E into E be an embedding of E into itself over capital F. Then sigma is onto and hence an automorphism of capital E. Everybody knows that automorphism means a an isomorphism whose domain and codomain is same. An isomorphism whose domain and codomain is same is called an automorphism. So here already they given that sigma is an embedding. Embedding means it is a homomorphism into K into itself. So we are going to prove sigma is onto and hence it forms an automorphism. So right. Let capital E be an algebraic extension of F and sigma maps E into E be an embedding of E into itself. By the definition of embedding, sigma of alpha is equals to alpha for all alpha belongs to F. We have to prove that sigma is onto. What is the definition of onto? Every element of the codomain has at least one pre-image in the domain. Every element of the codomain has at least one pre-image in the domain. So that is, for given B belongs to capital E codomain, there exists an element A belongs to E domain such that sigma of B is equals to A. Now let us take an element A belongs to small e. Since E is algebraic extension of F, this element A is algebraic element over capital F. Obviously, A is an element of E. Small a is an element of E and this E is algebraic extension of F. So that element A is algebraic element over the field capital F. So if the element A, that element A is algebraic. A is algebraic over capital F. A is algebraic element over capital F. By applying the algebraic element definition, there must be a minimal polynomial P of x satisfied by that element A over the field capital F. Right. Let us take A1, A2 and so on AR be the set of roots of P of x that lies in capital E. I am defining some roots A1, A2 and so on AR. They are roots of the minimal polynomial P of x in the extension field capital E. That roots lies in capital E. Then A belongs to E is 1 among A1, A2 and so on AR. Excuse me. A belongs to E is 1 among A1, A2 and so on AR. Now define E dash is equals to F of A1, A2 and so on AR. E dash is generated by F and the elements A1, A2 and so on AR. Since the elements A1, A2 and so on AR are algebraic over capital F, by using previous definition, this E dash is an algebraic extension of capital F. So remember this point. Now let us define the polynomial P of x like this: alpha naught plus alpha 1x plus and so on plus x power n, where alpha I belongs to capital F. Suppose if u is root of P of x, then alpha naught plus alpha 1 u plus alpha 2 u square plus and so on alpha n minus 1 u power n minus 1 plus u power n is equals to 0. Now taking sigma on both sides, sigma of alpha naught and so on is equals to 0. Because of sigma is an embedding, it means it is a 1 1 and remember that embedding means it is a 1 1 and homomorphism mapping. It is a 1 1 and homomorphism mapping. So that's it. So this sigma can be applied to individually every element, sigma of alpha naught, sigma of alpha 1 u and so on, sigma of alpha power n is equals to 0. And then already we defined that sigma of alpha is equals to alpha for all alpha belongs to capital F. Here these are all scalars: alpha 1, alpha naught and so on, alpha n, alpha naught, alpha 1 and so on, alpha n minus 1. These are scalars in the field capital F. So by sigma definition they can be written as alpha naught, alpha 1 into sigma of u, alpha 2 into sigma of u whole square plus and so on, sigma of u power n is equals to 0. This condition shows us if A is a root of P of x, then sigma of A is also a root of P of x. If A is a root, then sigma of A is also a root. So generator of A1, A2 and so on AR is equals to generator of sigma of A1, sigma of A2 and so on sigma of AR. Now f of A1, A2 and so on AR is equals to f of sigma of A1, sigma of A2 and so on sigma of AR. Suppose it is equivalent to beta, then it is equivalent to sigma of beta, which is equals to sigma of f of sigma of A1, sigma of A2 and so on sigma of AR. So we conclude that capital F of A1, A2 and so on AR is equals to sigma of f of A1, A2 and so on AR. It means sigma maps E dash into E dash is onto and E dash is subset to capital E. Therefore sigma maps E into E is also onto. Already it is an embedding, means it is both 1 1 and onto. Now it is an already it is an embedding, it means both 1 1 and homomorphism. Now we show that sigma is onto. So sigma satisfies all the three properties of isomorphism, and domain and codomain is same. Therefore sigma maps capital E into E is an automorphism. This completes the proof of our theorem. In the next video, we start algebraically closed fields. Keep learning. Wish you all the best.